Welcome to a new episode of the ITU Journal webinar series, where you can find insights and forward-looking research on future and evolving technologies. The ITU Journal is an international journal providing complete coverage of all communications and networking paradigms, free of charge for both readers and authors. This publication considers yet-to-be-published papers addressing fundamental and applied research, building bridges between disciplines, connecting theory with application, and stimulating international dialogue. Its interdisciplinary approach reflects ITU's comprehensive field of interest and explores the convergence of ICT with other disciplines. We count on your support to make this webinar an interesting experience. Please submit your questions to the speaker using the live video wall feature. All questions from the audience will be taken during the Q&A session after the talk. The webinar is being recorded, and the recording will be made available on the ITU Journal Webinars series playlist on YouTube. We hope that you will enjoy the talk, and we encourage you to stay connected until the end for the Wisdom Corner. Live lessons. I will now give the floor to our Master of Ceremony.
Hello, and welcome to the webinar series of the ITU Journal on Future and Evolving Technologies. My name is Alessia Magliarditi from ITU, the International Telecommunication Union, the United Nations Specialized Agency for Digital Technologies. It is my pleasure to open our second webinar of the season, kindly hosted by the Eye for Good, as part of the ITU Journal Discovery Series with Professor Yasaman Ghazanpour from Princeton University. So after the Q&A session, as just announced by our avatar, I will moderate the Wisdom Corner, live lessons. So please stay online. Our speaker agreed to a personal chat. She will share with us some lessons learned over the years that might perhaps be useful for some of you. I'm pleased now to introduce Professor Ian Akilditz, Editor-in-Chief of the ITU Journal and founder and president of Truva from the United States. Professor Akilditz is Ken Byers Chair Professor in Telecommunications Emeritus at the Georgia Institute of Technology. He has established many research centers worldwide, including in South Africa, Spain, Saudi Arabia, and Finland. He's Editor-in-Chief Emeritus of Impact Factor journals, highly cited and at the top of the most prestigious international rankings. Ian is visiting distinguished professors in several universities around the world. His current research interests are in 6G wireless systems, terahertz communication, metaverse, and communication in challenged environments. So Professor Akilditz, the floor is yours for your opening remarks and to introduce our speaker and then moderate the Q&A session. Thank you.
Thank you, Alessia. Thank you, really. It was very nice. And thanks to you all for joining us. Greetings to our distinguished global audience connecting from across the world. From Abu Dhabi, it is with great pride that we continue Season 5, Episode 2. This is our second speaker this fall of our ITU, International Telecommunications Union Journal on Future and Evolving Technologies, in short form ITU JFET webinar series. This webinar is dedicated to the pioneers who are not merely observing the technological landscape, but are actively architecting its future. Today, we are immensely privileged to host one of the most influential minds of her generation for his endeavor, Professor Yasaman Ghazanpour. As we commence, let us reflect on the core mission of our journal, founded in 2020 with a transformative vision. The journal was established to dismantle the conventional barriers between academic research and industrial application. Our objective is both clear and ambitious: to propel global innovation by cultivating deep, synergistic research at the very cutting edge of technology. The journal's rapid ascent to a position of scholarly excellence is a direct result of an extraordinary team. I extend my profound gratitude to Susan Ona-san, Bilal Jamusi, Alessia Magliarditi, you just saw her, and heroes in the background, in the backstage, Erika Campilongo, Maria Otero, and Pauline Nash, and our many dedicated colleagues whose unwavering commitment has forged the journal into the respected international institution it is today. So as you see, I'm fighting with my glasses. I'm trying to avoid it, but that's life. So yeah, I cannot survive without the glasses. Anyhow, we extend our formal invitation to the global research community to contribute your groundbreaking work or your technical papers to our journal, and to propose special issues on the topics that will shape tomorrow or tomorrow's. Your pioneering ideas are the very catalyst of our collective advancement. It is now my honor to introduce our featured speaker, or today's speaker. Dr. Yasemin Gasampur is an assistant professor of electrical computer engineering at Princeton University, where her research program is dedicated to pioneering next generation wireless networks and sensing systems. Her work is characterized by fundamental innovations in physical layer design and link layer protocols for emerging wireless platforms. Yasemin's academic pedigree includes a Bachelor of Science degree from Sharif University of Technology. As you may know, this is the top university in Iran. And, my personal experience is when you talk to the people, everybody says my university is top in my country, but Sharif is really a top university in Iran. And MS and PhD degrees from Rice University, which is also one of the top universities in the USA. Her advisor, Edward Knightley, is a dear friend of mine over 33 years now. And his advisor was a very good friend of mine, Domenico Ferrari. Thanks God he's still alive. He's like 1938 born, so he's like what? So he lives in Italy since a long time at UC Berkeley. So she's the grandchild of Domenico Ferrari. So also Edward is very, very successful, as some of you know, or many of you know. So Yasemin's career is decorated with a formidable array of the field's most prestigious honors, including the Zhengyi Wang Prize 2026. It's a brand new award, it looks like. The Princeton Early Career Faculty Award 2024, and Air Force AFOSR Office of Science Research Young Investigator Program Award 2024, NSF Career Award 2022, and Marconi Young Scholar Award 2020, an award for excellence in teaching. So these are all prestigious awards, by the way. So because there are so many awards on the market that it's a shame that some people use those as kind of awards, but these are real awards that we should all be proud of her achievements. Her status as a preeminent leader is further confirmed by her selection as a U.S. delegate to the National Academy of Engineering EU-US Frontiers of Engineering Symposium, and her recognition by N2 Women Engineering as one of 10 rising stars in communications and networking. The caliber and impact of her research are unequivocally demonstrated by multiple Best Paper awards at the world's most competitive conference, including US NICS and STI, ACM Mobicom, ACM Census. By the way, I was co-founders of these conferences, 1993 and 2003. And IEEE, I don't take credit for IEEE-WCNC. I have nothing to do with it. So I'm proud of a member of these Mobicom and Census committees. So Yasemin's influence extends significantly into professional service and leadership. She serves as co-director of the Princeton Next Generation Industry Affiliates Program. It's really fantastic. At such a young age, she did all these. She achieved all these incredible accolades in her career so far. She contributes to the technical program committee of premier ACM SIGMOBIL conferences and holds editorial board positions for Nature Communications Engineering, IEEE Transaction Wireless Communications, IEEE Communications Magazine, and IEEE Journal of Infrared Millimeter and Terahertz Waves. So I can imagine how happy she is that she's serving on all these editorial boards, and because that's the recognition of her achievements, right? But then she will come to an age, she said, I don't want to do these things anymore. But there are people in my age that are still doing it, so I don't know why. But anyhow, let's continue. In a powerful testament to the tangible impact of her work, Yasemin's contributions are enshrined in the Smithsonian Institution's Museum of Natural History, solidifying her legacy as a truly transformative innovator. Dear Yasemin, we are deeply privileged to have you with us. The platform is yours. We eagerly await your insights. Again, thank you for accepting our invitation. We really look forward to listening to you. Thank you.
Thank you so much, Ian, for the nice and long introduction. I'm really honored to be one of the speakers in this webinar series. Thanks a lot for inviting me. And I'm super excited about our conversation today. Looking forward to the Q&A after the talk. So let me go ahead and share my screen. Okay. Hopefully you can see it in the full screen. If not, please let me know. So today I'm going to talk about some of the research that my group has been doing at Princeton over the past couple of years. The title, as you can see, is From Foe to Friend, Physics-Driven Millimeter Wave and Sub-THz Wireless Networks. So wireless technologies have always been driven by applications and the need for higher data rate, lower latency that these applications would need. For 5G specifically, we targeted wireless, virtual and augmented reality, autonomous and connected cars, collaborative robotic systems and autonomous systems. These applications have one thing in common, and that's the need for multi-gigabit per second connectivity and ultra-low latency. However, my good mentor and previous dean, Andrea Goldsmith, has a saying that promises and pie crust are made to be broken. Of course, this is from Jonathan Swift, but what Andrea added is that especially in wireless network. So I really resonate with this. And today in this talk, I really want to get into the bottom of that, why we kept basically promising higher data rate. And in this past generation specifically, it was not really achieved. But before that, let's get us into two of the main keywords I had in my title, millimeter wave and sub-terahertz. Let's first basically explain what is so special about this part of a spectral regime that my group and many others, especially Ian as one of the pioneers, really looked into this spectral regime for next generation common sensing. So if you look into this figure, you can see this part of the spectrum is nicely placed between the lower frequency microwave regime. When you get low resolution in sensing larger wavelengths, you have a few hundreds of megahertz of available bandwidths at the best case scenario. And on the other side, where basically the infrared and the visible light regime, where you basically can have large swaths of available spectrum, but it's mostly line of sight only, and it does not really do well in terms of coverage and reflection. So this spectral regime can provide gigahertz scale bandwidths, which basically tells us that we can achieve gigabit per second scale connectivity. It has millimeter or sub-millimeter scale wavelengths. That means that we can do really high resolution sensing and imaging. I can have line of sight and a little bit of reflection, non-line of sight that becomes really handy sometimes. I can really create narrow beam widths. I can control the propagation of waves in a space by placing basically large antenna arrays to some extent. We'll talk about that in this talk. And these are all very important because then the sensing and comm can go hand in hand. I can really use the sensing capability of my wireless signals to get an understanding of what's going on in the environment. Let's say detect reflectors, detect blockers, and then use that information to improve communication. The sensing as is also a key additional incentive to put this millimeter wave sub-terahertz chips in future mobile devices that can add additional basically avenue for like a financial case for these companies to move forward with these technologies. As Ian mentioned, I'm also a co-director in the Princeton Next Industry Affiliate Program. So when we talk to our industry partners, the stakeholders in the field, that's the conversation we always have, that we really need to think about going beyond basically having cellular networks as a utility and think about other basically financial cases for this future system. So that can be one potential. Okay, so well, I told you that this multi-gigahertz scale bandwidth can provide gigabit per second, but that's only in principle, right? In practice, it's much harder. And the reason is basically the physics of wave propagation, right? As you go to the higher spectral frequency regimes, the loss of transmission over the air is really higher, right? And that higher spreading loss means that now you have to build very directional links that usually require large scale antenna arrays to really point your beam, point all of your energy into a specific direction where the user really is located at, right? We can do that, that's great, in principle it works, but really in terms of the system challenges, we have to think about the power consumptions of this system. We have to think about, okay, this link can be really established in a beautiful way, in a narrow way, but what if the user starts moving? Then how do I deal with that? Blockage is a second problem. Again, this frequency regime, because of the small wavelengths and higher absorption losses, when it interacts with like everyday objects, you get very high absorption loss. And that means that you cannot penetrate through wall, but you can also not penetrate through trees and human bodies and like furnitures in the room. This is a demo by T-Mobile from a few years ago that shows like a glass door can really block these millimeter wave signals, while the 600 megahertz holds strong, right? So even though 600 megahertz does not provide the gigabit per scale data rate I was looking for, but in terms of robustness, in terms of coverage, it has definitely advantage over millimeter wave signal. Now, sub-terahertz will be only worse, right? So it's even higher in spectral regime. So all of the things I mentioned about millimeter wave only gets worse in the sub-terahertz regime. Usually for blockage, the current solution is, once the blockage happens, let me try to find a plan B. Let me try to find an alternative transmitter or reflector in the environment, which may not be always available, or the cost of adopting a second transmitter is not really a small amount, right? In terms of deployment, but also in terms of spectral efficiency. So like to summarize, all of these solutions is basically saying, let's just adopt what we have at lower frequencies, scale them up and hope it works out. But at the end, in reality, we are battling with the physics of the problem. The physics of wave propagation is much, much harder to deal with in this higher spectral regime. So what I'm hoping to talk about, the message I'm trying to come across is the fact that we have to leverage this physics itself to design our next generation systems. So that's why I call it physics-driven millimeter wave and sub-terahertz communication and sensing system. So I'm going to talk about first how to leverage the physics for designing a new architectures in the physical layer, especially for beam forming and beam adaptation, and to reduce the power consumptions of this system. Then I'm going to talk about how to deal with the blockage issue that I just talked about, again, using the physics of wave propagation. And once we solve these two problems, I'm going to show you that this spectral regime is really exciting for unprecedented sensing application. So beyond communication, if I have this sub-terahertz chipset available in my mobile phone or as a battery-powered low-cost sensor, I can really do cool things about it. I'm going to give you two examples. One is in fruit quality sensing, ripeness sensing, and the second one is in robotics. So we'll talk about that hopefully toward the end of the talk. Okay. So let's start with the first category, physical layer architectures. For this, I want to specifically talk about power consumption as the main issue. Why power consumption is a big problem here? There are two reasons for that. One is when I want to generate and amplify signals, that power consumption for that actually scales with the carrier frequency. So it's going to be very power intensive above 100 gigahertz. Number two is I told you that we really need directional beams to overcome the higher spreading loss over the air. Basically, having these larger scale complex time shifting or phase shifting arrays is also costly, power demanding, and hard to fabricate. It's important to note that higher power consumption also was an issue with millimeter wave mobile operation, and it's going to be again a bigger issue in sub-THz. So is there any hope for above 100 gigahertz? Can I ever have smaller scale battery powered sub-THz node that consumes little power, maybe for mobile operation or maybe for IoT sensors? Is that even possible? So for that, I want to talk about a concept called backscattering, which many of you might know. Backscattering is the common technology used for IoT operation right now at lower frequencies. The way it works is instead of having the sensor generate a signal and transmit it, you'll have the sensor piggyback its information on an ongoing transmission, on an ambient signal that is being sent by a powerful node that is maybe plugged in, right? And that basically saves a lot of power because you don't generate that signal anymore, right? So the value of that for sub-THz, you can imagine that's really valuable, right? A simple way of thinking about it is that if I have a very low cost, low power sensor that basically reflects the signal if it wants to send bit 1 and does not reflect the signal if it wants to send bit 0. So by just having a switch that reflects or not reflect, I can piggyback my information on the ongoing transmission. So this is very well known. However, existing technologies are often at a low sub-6 gigahertz regime. There has been some effort in scaling that carrier frequency to higher regimes. I'm showing a few examples here. Unfortunately, they're either very narrow bands or they use active phase conjugating arrays, which itself is power demand. So when we started this, we actually asked for 3 key requirements for these directional backscattering networks above 100 gigahertz. Our first requirement was that we wanted to be directional for sure, right? Because there is no hope for closing the link and getting away with the link budget if you're not doing directional. In backscattering, it's even more important because you have ultra power of 4 losses, ultra power of 2 for your forward direction and another ultra power of 2 for your backward direction. So you really need to be directional. We wanted our design to be low power, ideally passive, but ultra low power if possible. And we wanted this to operate on a wide bandwidth because we are, at the end of the day, moving to these higher spectral regimes because of the availability of wider bandwidths. So with these 3 requirements in mind, we designed a new backscattering architecture. We called it Likia scatter. It's a novel node architecture that supports frequency agile directional backscattering. We first basically published this in 2023 in an STI that got the best paper award, and then the extended version was submitted to Nature Communication, published there a year later. So let's talk a little bit about the fundamental principle of this new architecture, right? For that, I have to introduce a relatively new type of antenna that I started working on at the final year of my PhD at Rice. It's called leaky wave antenna. So it's nothing scary. It's basically a waveguide where you can create it by putting 2 metallic plates in parallel to each other and have an open slit on one side of this waveguide. What happens is if you send the signal inside the waveguide, when it reaches that open slit, leaks out to the space, to the free space. That's why it's called leaky wave. But interestingly, it leaks out at a specific angle that is correlated with the frequency of that signal. It can be, I mean, I'm gonna skip the physics of waveguides here, but you can basically have a monotonic equation that shows the relationship between the angle at which the signal goes and the frequency of that signal. And you can see that higher frequencies emit at lower angle and vice versa. Lower frequencies emit at larger angles. So this is exciting because I don't need the larger scale phase array anymore to tune the angle at which I want to send the signal to. I can do that by doing frequency controlling, right? And I want to note that even though I'm showing a bulky waveguide here, you can actually go ahead and design this and an integrated CMOS chip. My colleague at Princeton actually did that in 2021. And you can see this is a 1mm by 3mm chips, very compact. Okay, so once I have this, then I can do kind of start thinking about a lot of cool applications of such an antenna system in wireless communication and sensing. One quick thing that comes to mind is that these devices are great for localization. So if I send the wideband signal in, as I said, different frequencies go to different angles. So it creates some form of an invisible, basically, rainbow, terahertz rainbow, we called it, that gives you a mapping between frequency and angle, meaning that if I put a receiver, based on the frequency that that receiver is detecting, I can figure out the angle of that receiver relative to the transmitter. So I can do localization, at least angular localization, right? And I can do it with one antenna at the transmitter and with one measurement, with one basically in one shot. And I can do it for many receivers at the same time because all of them can do the same independent of each other. Now, the key thing that we leverage in this new antenna system is the reciprocity. So the angle frequency relationship I told you about, each frequency goes to an angle, it's reciprocal on the receive side, meaning that at the receive side, if I look at the set of frequencies that is impinging at the device, only the frequency that is impinging at the right angle is going to couple into the waveguide. So this is the measurement result we showed. We basically switch the transmitter receiver, and you can see we get the exact same power versus frequency profile, right? So this is perfect. This reciprocity can really be helpful now in creating a retro-directive link. So on the high level, my tag has this leaky wave antenna, and instead of one slit, it has two slits. Let me tell you how it works. If I have a basically powerful transmitter that knows where this tag is, it basically chooses the right frequency to communicate to this tag. That frequency will couple into the waveguide. Internally, I will just put some millimeter or micrometer mirrors to guide the signal to the other slit. And then because the frequency has not changed, that frequency will emit out to the same angle. So it goes back directly to the angle it came from. Hence, we call this a retro-directive link, right? So I got this retro-directivity in a passive way, so zero power cost, and with a device that is low cost and compact. So let me show you some measurement results. So you can see in our experimental setup, we have a terahertz transceiver. So that's the device that is transmitting and receiving wireless signals. And I have my low power terahertz backscatter node on the left side. In the figure, I'm showing basically the angle of reception is the same that angle of impinging. So that retro-directivity is being held. In the inside, I'm showing the radiation pattern of this reflected signal, just to show that these are super directional. You can see that these are really pencil-shaped beam and with very high 30+ dBi directivity. So this is the result we published in Nature Comp. We also looked into the bandwidths that these devices can support, because as I told you, one of our requirements was supporting wide bandwidths. And interestingly, the bandwidths that they can support is also dependent on the location of the tag relative to the transmitter. And that's coming from, again, the derivative of the equation I showed you earlier. But regardless, you can see that at the worst case scenario, I can still support a few gigahertz of bandwidth, which is enough for the kind of application I have in mind. So this very simple architecture that is very different from the conventional phased array designs can now support or meet all the three requirements that I had. Now, I told you how to create these directional links, but I haven't told you really how to modulate your data on top of the signal. For that, we first started with the most, I guess, simple thing, and that's using MEMS mirrors or MEMS switches to do amplitude and phase modulation. Specifically, I basically replaced the two mirrors I showed earlier with two MEMS switches. And if I move the first mirror laterally, it will basically create a small, like a small amount of movement will create a large amount of phase shift. And that's because the wavelength is really small in this regime. And the second mirror can be rotated like this, and that will basically change the amount of guided wave that sees the second aperture, or the amount of power at the end that is leaking out of this second aperture. And that gives me amplitude modulation. You can see in the figure in the bottom, like EM simulation of that if it's rotated a little bit, you can see that the wave is kind of missing the second aperture or half of the second aperture, so the less power will leak out. We did experimental demonstrations of that. So we did various complex modulations at different frequencies, all at the same time, using our Likia scatter nodes. Now, another way that you can modulate the signal. So the problem with these MEMS switches is that you cannot miniaturize them beyond a certain scale, right? It's also very hard to scale, and it's mechanical, so it might be slow, and it can get mechanical fatigue over time. Alternatively, my colleagues and myself at Princeton, we looked into a new classes of wideband switches, and these are electrochemical switches that can modulate terahertz signals. They are ultra low power, and they basically support, you can see, a very wide spectral regime from like 100 gigahertz to 1 terahertz. I'm not going to go into the details of that, but on a high level, the way it works is that you have an ionic channel. When you apply a bias, your ion moves from that ionic channel to your organic film and changes the conductivity of that film. So then when the conductivity is changed, then the amplitude or the amount of absorption and reflection of that organic film, which is a polymer, will also change. And that's what we use as a switch. This is amplitude modulation only. We are looking into new ways of doing phase modulation now with these switches. And this is basically a very recent work. You can see Advanced Material 2025. And this is the first time this electrochemical switches has ever been used for terahertz modulation. So we are excited about this direction moving forward. Okay, so now if I can have this low power nodes, I can think about a complex industrial setting where I have terahertz IoT nodes being connected to a terahertz reader and all being operated at the same time. Now, I want to point out that I can have many IoT nodes with that structure in mind, because I get basically two inherent way of interference mitigation. One is because these links are directional, they are not interfering with in a space, so it's a space division multiple access. And because depending on where the tag is, it modulates a different portion of the impinging signal, I get also by design frequency division multiple access. So you can see some numerical numbers. I can easily support thousands of concurrent links with this type of technology. Okay. This was basically an example of using physics to design new physical layer architectures. Let me move on to the second portion of the talk, and that's providing seamless and resilient connectivity, especially when you have blockages in the environment. I want to maybe start by saying that the concept of seamless connectivity has changed over the years. Pre-millimeter wave in maybe LTE, even 3G, when we talked about seamless connectivity, we basically meant, or if I have mobility in the system, how do I do a smart handover? So my call, the quality does not drop, basically. But in the millimeter wave sub-THz, because you get blocked very easily by everyday objects, this means that you have to have a mechanism for fast reaction. You need to be able to detect this block and react to that in a very real-time manner. So it's a more challenging problem, if you like. So there are two things that we have to accomplish. One is that there will be a blockage in the next X a millisecond, microsecond, depending on your resolution, so that I need to do something about this. So that detection is really challenging. I don't want to go into the details of that. Our group is working on that, but for the sake of time, let's assume that problem is solved. Let's say I have a camera in the room, and it's detecting all the users, all the mobilities, so I can have close to real-time information about the dynamics of my environment. Now, even if I know that, the question is, how do I maximize the reception or the signal quality under this blockage information? And that's what I want to talk about today. Naive ways of doing that is that, okay, I know the signal is going to be blocked, and I know there is a wall here, so I'm going to bounce my signal over this wall to reach the client. Or I know there's a second base station nearby, I'm going to ping it to see if it's available to serve these users. Or I can fall back to basically low frequency regimes, use legacy bands for that. While these techniques have been implemented to some extent even in today's millimeter wave 5G, there's no guarantee that they work in practice, in a sense that that reflector path might not exist. The reflector path might not be strong enough. That other base station may be busy if it exists, serving other users. Legacy band may be busy again. So you need to have spectral efficiency in mind when you are designing your networks. So let me add to that in this higher spectral regime, we are also entering a new uncharted territory. When I put large scale apertures and my wavelengths is small, the near field range of my transmitter can extend to tens of meters. And that may pretty much include a large conference room, a lobby of a hotel. So many indoor environments might basically be experiencing near field communication only. Just to give you an example, if I have a 10 centimeter aperture at 5 gigahertz, my near field is about 30 centimeters. That's why we didn't really care about near field in the older generations of wireless. In the higher frequencies, let's say D-band, 140 gigahertz, that can be 14 meters. Now, the access point and base station may host users that are in the near field and in the far field, and the interplay between them is actually really interesting. So, is the near field a challenge or a problem? Actually, our view, in the research community, the answer to this question has changed over the years. First, as I said, we started by saying we don't really care about it because we don't see a near field, like extended near field range in lower frequencies. Then we said, okay, maybe it distorts my signal a little bit. Let me do pre-distortion, pre-calibration, or post-processing to deal with that. More recently, we said, actually, this near field is cool. We can use that near field property to focus my power into a specific point in a space and improve my signal to noise ratio, or make the communication more secure, or actually do other things like wireless power transfer. What I want to talk about is actually we can do much more than focusing in this spectral regime. It's a new exciting design space for us actually, because we can control how waves propagate in depth and also in angle. So I can create exotic beams like the zigzag beam I'm showing here. And some of these exotic beams actually have nice property for blockage recovery and blockage resilient communication. For example, Bessel beams can heal after they encounter a blockage, and airy beams or curved beams can go around an obstructions. They can create non-diffracting region in certain part of the space where we think the user might be located at. So if we think about the evolution of the how we think about radiation, before 5G, it was mostly no directivity, omnidirectional transmission. Millimeter wave was about directional connectivity. But after 5G, in the sub-THz regime, we can actually go beyond that and think about beam shaping, as I said, controlled not just the angle, but also the depths of our radiation. So I want to talk about one of the projects we've been working on. We have a lot of ongoing and past efforts in this line of work, but let me just give you one example so that you can get a taste of what can be done. So I want to talk about using curved beams. So for you might ask, like, Yasaman, this is against the physics I know from my high school or from my undergrad. Light does not curve. Like, what are you talking about? Well, you're right. Light does not curve. EM waves do not curve. But if I put many antennas, then I adjust the phase or delays of each of them. In the near field, I can make them as constructively on a curved trajectory. So a single antenna cannot give us curved trajectories. Many antennas together can. And if I can have that, then I can curve around obstructions. Basically, simulation tells us that if I have a small blockage here, if I go from beam focusing to use of these airy beams, you can see the shadow area behind the blockage, that blue region I'm showing in the top heat map, can be really reduced. Okay, so as a system designer, the question that I have is, okay, these are very interesting in theory, but can you really implement that using phased arrays, using commercial platform, using meta surfaces, or do you need some exotic structure to really create these beams? Fortunately, you can actually create this curved beam by phase manipulation only, and you don't even need a very high phase resolution. With 2 or 3 bits, you can create a very nice curved beam. Okay, so I can create them. That's great, problem solved. Actually, no. One big challenge here is that how do I find the best curve trajectory? And that's a very hard problem to solve, because if I have 2 points in the space, there's only one line that connects them. But if I tell you connect this with curved or parabolic trajectories, you can find infinite number of trajectories, right? Now, which one is better, right? There's no closed form equation that tells you the received power under blockage under this curved trajectory. So there's no easy way to calculate it. You might say, okay, I can run EM simulation. Sure, you can run EM simulations, but if you really want to look at the scale of the problem, EM simulations for this scale may take even days to complete, right? So it's not very simple. You can find a geometric solution, maybe. You can give this problem to a mathematician and he can tell you, oh, this is the best trajectory. We haven't tried that, but I tell you that mapping a given geometric trajectory to a phase profile that can create that trajectory is also not simple. And not all trajectories can be actually realized in practice. So it's a very high dimensional problem without closed form equation. So the first step toward this actually to design a better, more efficient simulator. And I don't want to go to this in detail, but I just want to say we have designed a computation efficient near field simulator. That it's open source. You can go ahead and try it out. It gives you nice features to control about the environment, the transmitter. It has some built-in function for Bessel beam, airy beams. It can even you can put in an RIS event there. So this is an IEEE paper this year that got the Best Paper Award. Again, the link is there. Go ahead and try it out. If you have feedback, questions, feel free to reach out. But using this simulator, now at least I can do EM simulation fast and I can generate a data set. So with that in mind, we put together a physics-informed AI for AD beam optimization. And the idea is, if I have the abstract of the environment and I know from the physics which beam can be generated, what will be the trajectory of that beam to some extent, maybe in the line of sight without the blockage, I can put together my knowledge and have the AI predict the best beam under a given blockage setting. So this is, again, something we published this year. There's a lot of details in the design of that physics-informed AI. So the AI is not the black box here. There's physics in the input, output, in the way that we're designing this. So you should go ahead and check it out. But I want to show you a little bit of the result, like what can be done with this curved beams. So first of all, how much improvement in SNR we are talking about, in the receive power we're talking about? Well, it's actually substantial. So compared with beam focusing, which is the best thing you can do in near field under perfect location information, you still get 3 to 4 dB improvement. Compared with the beam steering, the Gaussian beam steering, you get like 20 dB, plus 20 dB of gain. So it's substantial. You get most of your advantage when you have a higher blockage ratio, right? That makes sense. If I'm not blocked, then don't use AD beam. Go ahead and use your beam focusing. We actually did experiments with this beam using metal surfaces in front of horn antenna. This is at 140 gigahertz. We tried various bandwidths up to 15 gigahertz. And I'm just showing basically 2 examples of a radiation heat map being measured, overlaying them with the, basically what physics or mathematical calculation tells us. You can see it, I mean, I did the offset so that you can see the trajectories clearly, but you can see it actually nicely matches up. So you can indeed create these beams with even simple passive metal surfaces in the lab. Okay. And this is another heat map where I showed you as we are moving the receiver, the blockage is setting, I'm adapting my beam, and you see that the amount of improvement I'm getting under compared with beam focusing. Again, this is another result showing that without blockage, the bit error rate, of course, is better with focused beam, but as soon as you have blockage, your AD beam can provide much better bit error rate performance compared with the focused beam. And of course, if I go beyond blockages and I consider a multi-user setting, I can use same properties, curved beam properties, to manage or mitigate interference in multi-user setting. Maybe I can go around the user that I don't want to interfere with. So this actually opens up a lot of opportunities for near field as well as far field interference mitigation and multi-user communication. Okay. So the last part is talking about two sensing application, and I know that I have to finish in 10 minutes. I think I'm on time. So what I want to point out is in this spectral regime, sensing actually was talked about, as was studied before communication. These spectral regions have very nice properties in terms of sensitivity to certain gases, molecules, especially water and humidity. And there have been, again, I'm just putting the 5 textbooks on terahertz sensing that is available on the market. So this is a very old, I would say, and mature field. But what I want to talk about when I talk about sensing in my aspect is if I have narrow band terahertz signal, not the spectroscopy where you have few terahertz of bandwidth and you do very exciting, cool sensing applications. If I bring these chips into battery power devices, into my mobile phone, what can I do with it? What kind of new sensing application it will enable? So as I promised, I'll talk about agriculture and food sensing and then robotics. let me motivate the agriculture problem for a second. As many of you may know, food waste is a really big challenge, universal challenge. Half of the fruits and vegetables produced worldwide are wasted each year. The market is, in the US alone is $40 billion. But aside from the financial aspect of that, this is actually a very big problem, as we have many parts of the world dealing with hunger, and at the same time, we are wasting food, and especially fruit and vegetables are the #1 category in the food waste. So how do I reduce the food waste? One key aspect of that is measuring quality, so that I can then manage or optimize shelf time, transportation, all of those things. So I need to have information about the food and food quality. And there's no good solution on the market. You can have invasive solutions, or you can extract the juice of the fruit, for example, and get Brix measurement. It's going to give you sugar percentage. Or devices that are based on NIR sensor, you have to put them in touch with the fruit, and it's labor and cost extensive. So what we envision for this is, because a major part of the fruit is water, and sub-THz signal also resonate really well. They can extract information about water, humidity, and sugar very well. What if I shine a terahertz signal on my food, look at the reflection of that, and try to extract these ripeness metrics? Brix and dry matter are the two important ones. So you can imagine there are two applications, I think. One is I can put a sub-THz system underneath a conveyor belt setup, and I can then use a very wideband signal because it's plugged in. Or I can think about bringing this technology to the consumer, again, using a mobile phone that has this D-band chipset in it, and do sensing when I'm doing grocery shopping. This is very important because you really want to control sometimes your sugar intake or the quality of the fruit you are intaking. And from the technology side, the requirement is very different here, because now it's on the mobile device. It has to be narrowband. It has to be battery powered. So we did a larger scale testing. We did various fruits, 20 days in the lab. We did testing, and we had cameras, NIR sensor as kind of other baselines and ground truth metrics you might want to use. Then we looked at, okay, which part of a spectrum resonates with ripeness? Which part of the spectrum changes the most as the fruit changes over days, 20 days. And you can see it's all over the place. It's different for different types of fruit. And it's not a particular band that I say, this band is my golden band to do fruit quality sensing. It's not like that. So with the wideband can really be important because you get rich spectral properties. We put this data, and we developed a chemometric analysis of this. And again, the details of that, I don't want to go through that. But it basically gets the data, gets the ground truth label from the NIR, and it tries to then predict the Brix dry matter. There's no machine learning here. This is basically a partial least square regression here that we are doing. So it predicts the values of Brix and dry matter based on the spectrum it's measuring. And if I look at the performance in terms of prediction accuracy, I can see the predicted and measured values match pretty well for different types of fruit, avocados, green apple. We tried persimmon. But for example, the camera doesn't do a good job. The SSIM is for cameras. So camera detects color change, but it's not accurate. It's not high resolution. For some fruit, like for example, green apple doesn't even change color. So you can see it's like almost constant. So the average error was below 1%. This is actually negligible because our tongue, our taste actually has a higher error than that. So it's imperceivable by the consumer. Okay. Now, I said this is great, wideband, you can do a lot of things with it, good accuracy, 1%. But on the mobile phone, there's no way you can have 500, 600 megahertz of spectrum. What can I do if I make this narrowband? Of course, I'm going to lose data. I'm going to lose information. As I showed you, the information was all over the spectrum. But what I can do is And what we did is we designed specialized stickers that you can attach to the body of the fluid, and it will basically resonate the profile you're looking for and give you more information in a narrow band signal. On the high level, what we're doing is we're putting a resonating structure, and it's just a flexible, biodegradable sticker we design attached to the body of the fluid. It will create a peak in the spectral region we want, narrow peak, and as the fluid ripens, that peak starts shifting. That's kind of the high level. So if I read the peak value, I don't need to know the whole spectral profile. If I read the peak, I can map it to bricks and dry matter. We actually did a lot of analysis and modeling on this. We showed that you often see two peaks, and that's two different resonance modes, dipole resonance and propagating plasmon. And with that, we separated the peel information from the flash for the first time. So you can actually see the flash changing over time. This is important for food that have very thick layer in their analysis. So let me maybe jump into the results here. As I said, we use very cheap metal sticker using printer and aluminum foil to design this sticker. Again, we ran experiments. We use a terahertz transceiver for sending and detecting the signals, and we tested over different types of food. I'm showing that the peak actually changes. You can see the peak is decreasing over time, over hours. That's the signature we are using for ripeness sensing, and you can see the bricks can be measured pretty accurately for per ampere. For mango, we're not doing a good job. This is interesting because we went and then looked basically online, and it seems like the NIR sensor that we are using does not really provide good accuracy for mango, meaning that our ground truth was not really accurate for mango. Okay, so this is a paper again this year in Nature Food. If you're more interested in that, please take a look at that. So for the sake of time, I maybe skip over the robotic work and move to the conclusion. Happy to take questions on that, by the way, and happy to share the slides if you're interested in looking over terahertz for robotics as well. Okay, so hopefully in this talk, I could convince you that millimeter wave sub-THz are promising for next generation wireless communication and sensing because of their potential for multi-gigabit per second data rate. However, the physics of wave propagation is really challenging in this spectral regime. And instead of fighting with it and try to just scale up and just use our old or pretty mature technologies and just scaling them up, we should really think about leveraging the new physics that this spectral region provides into the design, from physical layer to math layer and even to our applications. Many assumptions should be revisited: near field channels, interference models, beam shapes, so on and so forth. We have to think about the power aspects and the robustness and resilience aspects of this communication systems. On the positive side, there are a lot of interesting sensing opportunities that can be added on as an add-on feature of this wireless signals can be leveraged, and of course they can be used to enhance the communication. As I said, I skipped over using wireless signal for blockage detection, but you can imagine if I can use these signals themselves to sense blockages and reflectors and kind of get an image of the environment, I can really use that information. The best part is there are many open challenges at the intersection of physics, AI, and wireless for motivated students and researchers to tackle. So it's pretty exciting time for wireless. With that, I want to thank all our sponsors and my research group at Princeton who really did the work, and I'm just here on their behalf to explain the amazing stuff they did. With that, thanks a lot and happy to take questions.
Thanks a lot, Yasemin. Really exciting talk, and especially I loved your energy and enthusiasm and presenting your research activities. And there are so many questions that I could ask you, and I'm also waiting questions from the audience, but let me start to say that you have really excellent directions in our research, and I could ask you so many questions, but let me just focus on this retro-directive core case. So this retro-directive mechanism is fascinating. And how does it handle multi-path components? In rich scattering environment, does the system risk creating multiple unintended retro-directed beams? And if so, how is this managed at the protocol level to avoid self-interference? So I hope the question is not too long, but I hope you can answer us.
Right. So great question. So let me start with the multipass for a second. So first of all, we are talking about sub-THz. So multipass is not really strong in this regime. But let's imagine I have a strong transmitter, I have this backscatter node, and there is multipass in the environment. Because I am, so if I'm sending even one frequency, let's say in an omnidirectional manner for a second, the angle at which the non-line of sight path reaches the tag, reaches the backscatter node is different from the line of sight path. And as I said, we have this angle frequency relationship. So if that frequency is not impinging at the right angle, it will actually not go into the waveguide. So the waveguide is kind of rejecting that frequency. So it helps with multipass rejection to some extent, right? Now, same for the return, right? The return path from the tag to the reader, it's actually very directive. I showed you the radiation patterns. So the chance of getting multipass is quite low on the reflection side as
well. I will jump to the audience question. Here is Taksin Akalın. He is our old-timer. He's from France. His question is, what is the highest modulation frequency or speed that you can reach with the electrochemical transistors approach?
Yeah, so great question. So the current electrochemical switches that we have right now with the fabrication technology at the university is kilohertz scale. Of course, these are like ions moving, so it's not going to be ever at the, I guess, multi-gigahertz level, but there are ways to push that limit. And we are basically working on some technologies that can advance that. I have to say that here, if you're considering an IoT node, the data rate is not really at the gigabit per second scale, right? So we really want to have large scale adoption, like many links at the same time, but each link is not going to be gigabit per second scale.
Let me ask you also another question of mine. So this is about self-curving beams. Actually, I'm also interested to know more about your fruit sensing case, but we'll come to that. It's really fantastic. Anyhow, so AI-assisted self-curving beams is a revolutionary idea that shows also like how forefront research you're conducting. So the question is, what are the primary inputs to the AI model? Because you talked about AI. And is it primarily channel state information, real-time RF imaging of the environment, or a combination? And also, what is the feedback mechanism? How does the beam know it has successfully bent around an obstacle to reach the intended user? So again, I have multiple sub-questions, but I'm sure you followed it.
Yes, great question. So here the input to the AI is a couple of things. One is we know how many antennas we have, and we know the phase shifter resolution. So we know hardware capabilities. And number two is we know that we are designing Airy curved beam. So the equation for the Airy beam is known. The physics of that is known by the AI.
Yeah.
The third thing is known is the environment. What does that mean? So I don't assume I know channel state information, because getting channel state information can be very time consuming. But imagine I have a camera in the room that detects like with new edge detection technology, you can detect, oh, there's an object here and this is the edge of the object, right? So I assume that information is known to my AI. So the dimension of the blockage and its location is known. but the receiver does not have channel state information. If you have channel state information, by the way, this is not a hard problem, right? Because you can always do conjugate, you can always use a lot of existing MIMO technologies and MIMO pre-coding that leverages CSI, but we don't want to assume we have CSI information. And now that's kind of the input to the AI. The output is the phase profile that I have to put on my transmitter. Very simple, right? To generate the curve. Now, in terms of the feedback mechanism, right now, you basically measure the power flow far at the receiver, and if it's above a threshold, you basically declare success for that application, and that's it. If you don't get power profile, power budget that you wanted, you have to send the information back to the transmitter, so the transmitter can do something else. The best ARRI beam that I could generate was not good enough for your application. Now what? Right? Then you can think about, okay, I maybe have to reduce the quality, let's say, of the video I'm transmitting, so the application need goes down, or actually I have to go and find another transmitter because there's no other way I can satisfy your application requirements.
But also, when you talk about channel state information, as you know, when the channel is dynamic, then you need to change your assumptions, right, for the input. So how do you deal with those cases, like for dynamic channel conditions? So what do you rely on? Because it's also time consuming and energy consuming. Don't forget it.
Yeah, great question. So as I said, there are two challenges, right? One is to have environment information. So an equivalent of that is channel information, right? And if I have that, now how do I use that information to maximize reception? So I talked about the second component in this talk. Now, the last thing is, how do you get that if you have real dynamic high mobility setting? How do you go around the first challenge? And you're right, it's not easy. I think what the community is moving forward is twofold. One is sensor fusion. So you can really think about using whatever sensors you have available, cameras, LiDAR, the wireless signals themselves, right? To detect dynamics of the environment. And the speed at which you can do that, of course, depends on the sensors that are available to do and many other things. Another potential route is basically AI itself, right? So if I have some knowledge of a person moving, let's say in a sidewalk, I know when this guy is gonna end up 10 milliseconds from now. It's no, so there is a structure in our mobility, right? And in our everyday mobility. So AI and the digital twin aided AI, I would say, can really be harvested and harnessed for predicting that. So you don't need to do real-time measurement because that's very power consuming, time consuming. But if I like once in a while do the measurement, but fill in the gap with prediction, that's going to be fascinating.
You know, I asked you this sub question, but maybe you answered it, but somehow I missed it about this. How does the beam know it has successfully bent around an obstacle to reach the intended user? So you mentioned about some threshold. So how do you do really realistically? So what is your threshold and how do you determine that? Because what I understood is you also said, when I determine this, I send the feedback or whatever. And so, but what type of feedback is that? So it's like retransmitted or what do you do?
Yeah. So in the measurement, by the way, this is not an end-to-end system yet. Okay? So we haven't measured that. But the way I envision it is you, under this obstruction, this AI platform will provide the best beam you can use to maximize power, right? Now you go ahead and transmit that and you measure power at the receiver, right? It's either satisfying for your application or not, for the MCS you're targeting or not. If it's satisfying, then you can send that feedback, go ahead, transmit. You can use a low frequency signal for that feedback that goes around, goes through the obstruction. That's one way, right? Because again, the receiver is blocked from the transmitter, right? So unless we are running the same AI at the receiver to find the curved beam to get back to the transmitter, there is no other way. So either use low frequency to get your feedback information to the transmitter, or you have to run a small scale version of this problem on the user device to find the curved beam back to the to the transmit. It's going to be harder because the aperture dimension at the receiver is often smaller. So the capability, the curving capabilities that you have at the receiver is going to be lower than.
You know, I have been told that we have almost 65 online users that are following us, which is really good because usually we put these webinars on our website and also on YouTube, and there are thousands of people there watching them. But usually we have much less number of participants. But unfortunately, we don't get questions from the audience. Maybe they're afraid of asking questions, but let me continue. It looks like you and I are talking, but I'm sure that the audience is appreciating it. So as I said, I have many questions, but so on the core trade-off, so the retro-directive architecture promises significant power savings. So the question is, what is the primary trade-off for this lower power? And is it a reduction in communication range, data rate, or something else like the complexity of the receiver on the user device?
Yeah, great question. So it's all of the above, right? I need to have a dual duplex transceiver that now transmit high frequency at any angle I want, right? And I didn't talk about that, right? That powerful transceiver needs to be plugged in. It's going to consume a lot of power, right? But if you are in a scenario where you again have thousands of nodes, you can afford to have one high power node getting data from thousands of low power. The total power consumption makes sense in that setting. But if you have, let's say, one tag, and you are consuming a lot of power at the transceiver to just support that one tag, of course, doesn't make sense, right? So it's more complex, high power consumption at the terahertz transceiver node for sure. The range is going to be shorter. We did some analysis. You can get to tens of meters easily on this. We have like a whole supplement on this in our NatureCom paper. But if you want to get to hundreds of meters, then I don't think this is that simple. At least if you want to be below the FCC limit, right? That's my assumption. Below the FCC limit, with this technology, what is the maximum range I can push it? It's tens of meters possible. So in the setting I showed, in an industrial setting, in many IoT nodes, on a large indoor environment, perfectly doable. Outdoor, hundreds or kilometer scale, it's going to be much harder.
So fantastic. Thank you, Yassam. And I have one more question, and I will let you go to Alessia. I'm sure she's waiting to ask you these personal, professional questions. So you also mentioned in the last slide about some changes required at the physical MAC layer, maybe also higher layers. But so what do you think that what type of MAC? I'm not asking you concrete answers, right? So what type of MAC and on the kind of routing layers that you need to some changes to fully leverage the capabilities of our near field, retro-directive, and self-curving beam systems.
Yeah.
Of course, it should be AI based, right? AI native and all that stuff. But what are your ideas or suggestions for the future research? Or are you conducting the research? I assume you do.
Yeah, fantastic question. So I think if you think about MAC layer protocols for previous generations, they deal with blockage. I'm talking about 11AD, 11AY. They deal with blockage in a reactive manner. And in the most basic thing, let's say basically they're saying, oh, every 100 milliseconds, let me do a sector sweep and then find the most updated beams. If the link is blocked, do beam training again, right? I think what we need to do if you ever want to have mobile connectivity at this higher spectral regime in reality is a proactive mechanism built in my MAC layer. How does that look like? It's an important question. But you basically want, as you're transmitting, you really want to make sure that you're tracking the user, right? So some aspect of joint command sensing has to be a part of it at some point so that you are doing your sensing as part of your MAC layer so that you can adapt in a proactive manner. I think that would be on the high level the way to go if you want to have seamless ubiquitous connectivity.
You know, I cannot let you go because I really enjoyed talking to you. A young
Yeah.
brain and full of this enthusiasm. So let me ask you one more. I'm sorry, Alessia. So one more question about your last part, that you are sensing these fruits, you know, the nature, right? So normally, all these natural phenomenon, they do chemical signaling. So you look from the, you know, our world, like electromagnetic, you sense things in the terahertz domain. But did you look at from their perspective, like from the chemical perspective, and then because you know chemical meets the electromagnetic area, right? So did you look at that direction also? That's my
No,
last question. I will not continue.
no, we haven't. I mean, that's actually a great suggestion. We basically modeled fruit as a multi-layer dielectric that absorb and reflect at each layer. And it's a complex multi-layer, of course, but how would the chemistry of that uh, basically deal with or interface with the EM wave? I think we require interdisciplinary knowledge about the biochemistry side combined with what we are doing to really answer that question. We don't know for sure, but I
Please
can.
work with my former student Massimiliano Pierabon. He also worked with Joseph, so you are working with Joseph. So
Yeah,
Massimiliano is the right guy for these chemical signaling, molecular communication. So that will be great to work with him.
yeah, yeah,
I
yeah.
hope you will meet each other and maybe you met. So anyhow, I really thank you, Yasemin. It was fantastic, really. I personally enjoyed it. I hope our audience also enjoyed it. Please let us know your feedback. And Alessia, Yasemin is yours. Please continue.
Thank you so
Thank
Thank
much.
you,
you.
Yasemin.
Thank you.
Thanks a lot, Ian, for moderating this Q&A session. And thank you very much, Professor Gazipur, for your excellent presentation. So now we move to the Wisdom Corner, live life lessons. So this is a corner which aims at offering a unique and special angle to this series of webinars, adding a personal touch. So I will start with my first question. Looking back on your journey, what is the most valuable life lesson or even a failure, if you want to call it this way, you have encountered that shape your path? And how can this lesson inspire those attending or guide those attending this webinar?
Okay, so now this is the hard part, right?
Yeah.
Okay, so very great question, by the way. So
Uh,
I,
can I jump in? I'm really sorry.
Of
Just for the
course.
audience. Uh, you know, these questions were not given to the candidate before or our speaker.
Yes.
It's not prepared. That's why our speakers are always like shocked in the beginning. So Yasemin had the same reaction. So don't.
Yeah.
It's not prepared, by the way. So this is just all spontaneous questions and answers. So just want to let you know.
Thank you, Ian.
yes, yes. So, okay, so I say that like if you are doing something that you don't encounter failure at all, that means that you're not challenging yourself enough, right?
Mm.
So I think if we view failures like that, we actually embrace it. We become happy when we fail. I say, okay, this is challenging for me, and that means I can grow in this. And I think we are surrounded by people that feel like they have their things together, they are all successful, and they know what you're doing. And of course, the social media around us is kind of contributing to that image to some extent. We always on LinkedIn, for example, we always see the success stories of like people are proud and excited about all the nice things happening there in their life, in their yeah, in their careers, and no one is talking about their paper rejection, their failed proposals, and this and that. So. Of course, that can be a problem, and that can give this wrong, I guess, image about failure, right? Failure that's like. So for me, I guess when I started my undergrad studies at Sharif, so it's the very top of school, I was like, okay, like what am I gonna do? These are all very smart people, and how do I survive here? same kind of question, same kind of feeling happened when I started my PhD. Now it's a new country, new language. Like, what do I do here? New ways of I remember I had a class first semester. I went to the class and I did not understand. The professor was talking too fast. I'm like, I may need to drop this course and retake it again next semester. Same thing when I started as a professor. I was very young, like 27, 28 years old. And I was thinking, okay, when they called me Professor Qasim, I'm like, doesn't sound right. The first time I went to meet our, I guess it was the welcoming reception for, I don't remember, undergrads, or I think it was for first year grads. I went there and our staff asked me to sign up in the sheet because they thought I'm the first year PhD student. For the reception. I took it as a compliment, and of course we had a lot of papers getting rejected and proposals getting rejected. And sometimes, I guess you reach a point and that if you know what you're doing is good, you continue doing that, right? For a lot of the papers and projects that got best paper award later, we started doing that before we had any funding. So I'm like, this is cool, let's do it. We're gonna find funding for that later. Don't worry about it, right? And I think that's the lesson I learned. Like, if you fail a lot, that kind of becomes routine, and I'm okay, this is good, I know what I'm talking about. And being a professor sometimes helps because you cannot get stuck in a failure. You have always a deadline coming up or something else coming up, so that helps you move forward with your career and don't get stuck. So if you are in that position right now, get yourself busy with something, with a new deadline, with a new adventure, and you will deal with that better, and you will basically get perspective about this failure in the future, and take it basically not seriously, I would say. Yeah.
Thank you so much for your very genuine answers. Actually, I really loved what you said, the value also of failures and what you can learn from. Thank you so much. What key advice would you give to young researchers, young professionals aspiring to build a career in academia? In your experience, what essential skills and qualities contribute to success in these fields?
Mm-hmm. So, okay, I can talk about this for an hour because that's the conversation I have with my students. But I'm going to keep it brief. So I think it's important to be rigorous in whatever you are doing, right? Always asking why. Like, I'm getting a good result. Let's not move on to the next experiment. Let's make sure that I understand the result I'm getting, right? We usually, when we get a good result, we move on. When we get a bad result, we're like, oh, what's going on, right? But I guess there's value in asking the why and going really deep into the problem you're solving, no matter what you are doing. So being rigorous and being curious is, I think, your number one priority or feature that makes you successful. Number two, I would say, is you need to find a good mentor. I was fortunate to have very good mentors throughout my careers. I think having a good mentor for emotional support, but also for technical support is really important, right? Along the way. So don't shy away from asking people. I would be delighted if someone says, oh, I look at you, like I feel that you can be my mentor. Like that's the best thing anyone can tell me that makes me happy, because then that's the real impact that I feel like I can have in someone's life. So yeah, so if you really admire someone's work, like a senior person in your field, like, yeah, reach out and say, can you be please my mentor? I need your help. I think that would be really a game changer in your career. And number three, I would say, is persistent, right? So persistent in whatever you're doing. And that's kind of connected to the first question, right? So I don't want to maybe repeat myself, but it's not enough to be smart. you need to be really persistent and resilient in your life if you want to get to the higher places. So learning from your mistakes, learning from your failures, embracing them, all the things we said for the first question applies here. So the three: being rigorous, finding a mentor, and really being persistent.
Wonderful. Thank you so much. Very, very useful what you shared. But what first inspired your passion for your field? And how did you turn this into a meaningful and impactful career?
Yeah. Okay. So this is also a hard question because it's kind of assuming that, as I said, we feel like people have their things together and figure things out from day one. That's why we ask this question, but that's not like that, right? So to be honest with you, I went to do electrical and computer engineering because I could not decide if I like math more than physics or the other way around.
Mm-hmm.
And someone told me, if you like them both, you should go do electrical and computer engineering because you get the good sense of both. And he was right. That's why I did EC. I did not plan to be a professor. I did not plan to come to US when I did that. So, but I can say that at any point in my life, this statement is true that I always did what I thought is correct, good. Even, I mean, I got advice from everybody, but at the end, I did the thing that I thought it's good for me, and the thing that I was passionate about, no matter the circumstance. So, and I think especially today, the field is changing so much, right? We have the speed of technology evolving is much faster than when I did my PhD. I think it's even was even slower when Ian and my advisor, like, they did their PhD. So if you want to really be on top of your field in this fast changing environment, you really need to be flexible and passionate with what you're doing. So I think that is the number. No matter what you're doing, just be passionate and be flexible.
Yeah. And among your career achievements, you have many. Is there one particular contribution, whether professional or personal, that has a profound impact on you or on others? And what makes this accomplishment especially meaningful to you? I think partially you answered already.
Yeah. I mean, I mean, you're not probably looking for a particular paper or particular contribution. So I think from maybe on a high level perspective,
Yeah.
I think when all of my students are kind of fantastic, and seeing them, even though they are fantastic, they are more fantastic now when compared with right? Kind of seeing how they grew over the years is really the most important and joyful experience of my career as a professor. And sometimes I tell them, like, remember day one, you were afraid of this, and now look at you, right? And that's really what I take pride in. And also, so that's on the mentorship and student aspect. Also, the next program that we are running, I mean, it started with kind of Andrea. I mean, Andrea had this idea, but then Andrea, myself, and Kaushik Sengupta, my colleague at Princeton, basically kicked this off 2 to 3 years ago. And the leadership aspect aside, being able to talk to real industry stakeholders that at the end of the day have to take this technology and adopt them and the business model out of it, and kind of understanding that translation and thinking about, okay, now that I know that, how did I take that into my problem definition, research problems? I think that is something I'm really proud of in our group, that we really have close collaboration with the industry, even though we are talking about very fundamental topics. You saw in my talk that some of them are very deep, some maybe not, cannot be adopted in the next 5 years or so, but really having that insight from industry incorporated to the research problem early on, I think that's what I take pride in.
Absolutely. Thank you so much. That was my last question. I really enjoyed this Wisdom Corner. I'm sure Ian enjoyed too, and all the participants. So thank you so much.
Of course, it was fun, and also I thank you for your honest and frank answers.
Yeah.
I mean, that's very lovely. I hope to meet you also in person and talk to you more. And I want to again remind you and also the audience. So we had your advisor here in the first season, Edward Knightley. He was one of our speakers, and one of your mentors, Vince Poor, was our first speaker. And another mentor who hired you to Princeton, Andrea Goldsmith, was also our speaker. So you are also our speaker. So you are also in the history of our journal and also our operation. Thank you, Yasemin, and
Thank you.
keep in touch. And I wish you the best with all your enthusiasm and everything. You have a brilliant future ahead of you. Stay safe and healthy, okay?
Thank
Bye.
you so much.
Thank you so much. Thank you.
And
Thank
I
you,
also thank
Professor Gasman.
my team in Geneva.
Oh, thanks.
Thank you, Alessia, and
Thanks, Ian. Thank you so
Erika,
much.
Maria, and Paulina, everybody.
And
So
I'll see you all
thank you.
online on the 25th of November
Yes, and we continue our
with
webinar.
Professor Pompili.
That's right, and it will be more on the underwater, I guess,
Yeah,
right?
exactly.
And then, so next season we'll have many, many more speakers. So that will be a very crowded season next spring and summer. So again, I wish you all a nice evening and keep in touch.
Thank you.